4.6 billion years ago, Earth didn't exist. There was no moon. There wasn't even the sun. Everything that would one day become our solar system, including every atom in your body, was floating through space inside a gigantic cloud of gas, dust, and tiny ice crystals called the Solar Nebula. For millions of years, this cloud drifted silently through the darkness. Then, somewhere nearby, a massive star reached the end of its life and exploded in one of the most powerful events in the universe, a supernova. The shockwave from that explosion slammed into the solar nebula, compressing parts of the cloud and triggering its collapse into gravity. As gravity pulled billions of tons of gas and dust inward, the cloud began spinning faster and faster, flattening into a giant rotating disk known as a protoplanetary disk. This is the reason almost every planet in our solar system still orbits the sun on nearly the same flat plane today. At the center of this spinning disk, pressure and temperature rose to unimaginable levels. When the core reached nearly 15 million degrees Celsius, hydrogen atoms began fusing into helium. Nuclear fusion had begun. The sun was born. Even today, that same fusion reaction powers every sunrise, every season, and almost every form of life on Earth. And although the sun formed from the same cloud as everything else, it captured almost all of the material. About 99.8% of the solar system's total mass ended up inside the sun, leaving just 0.2% to form every planet, moon, asteroid, and comet we know today. But how do you build an entire planet from only tiny grains of dust? The answer is surprisingly simple: collision after collision after collision. Inside the protoplanetary disk, microscopic dust particles constantly bumped into one another. Instead of bouncing apart, many stuck together through electrostatic and chemical forces. Over millions of years, these tiny clumps grew larger and larger in a process called accretion. Pebbles became rocks. Rocks became mountains. Mountains became objects several kilometers wide called planetesimals, the first building blocks of planets. Gravity then took over. These planetesimals attracted one another, crashing together repeatedly to form much larger bodies called protoplanets. Every collision released enormous amounts of energy, melting rock and creating vast oceans of magma. The modern theory explaining this process was developed by Soviet astronomer Viktor Safronov, whose ideas were initially ignored before later becoming one of the foundations of planetary science. Today, astronomers have actually observed similar planet-forming disks around young stars using powerful telescopes, confirming that this process is still happening elsewhere in the universe. Scientists have found even more evidence inside meteorites that fall to Earth. Many contain tiny spherical structures called chondrules, ancient droplets of molten material that formed before the planets themselves. Using radiometric dating of radioactive elements such as uranium, researchers discovered that some of these materials are even older than our solar system, proving they were forged inside stars that lived and died long before the sun was born. And after tens of millions of years of endless collisions, one growing protoplanet would eventually become our home, Earth. But the newly formed Earth looked nothing like the blue planet we know today. It was a giant ocean of molten lava, constantly bombarded by asteroids and planetesimals during a period known as the Hadean Eon, which lasted from about 4.6 to 4 billion years ago. Some of these impactors were over 100 kilometers wide, releasing enough energy to melt entire regions of the planet. Earth's surface was repeatedly destroyed and rebuilt, making it one of the most violent periods in our planet's history. Ironically, this chaotic era may have made life possible. Many of the asteroids striking Earth contained water locked inside minerals, while the original solar nebula also contained tiny ice crystals. Scientists believe that a significant portion of Earth's water came from these water-rich asteroids, although some water was already trapped deep inside the young Earth and later escaped through volcanic activity. Together, these forces gradually filled the planet with water. At the same time, countless volcanic eruptions released enormous amounts of water vapor, carbon dioxide, methane, and ammonia, creating Earth's first atmosphere. There was almost no oxygen. As the planet slowly cooled, water vapor condensed into rain. It didn't rain for days or months. It likely rained for millions of years, eventually filling Earth's first oceans. Meanwhile, something extraordinary was happening deep inside the planet. Because Earth was almost completely molten, its materials began separating by density in a process called planetary differentiation. Heavy elements like iron and nickel sank toward the center under gravity, while lighter elements such as oxygen, silicon, aluminum, sodium, and potassium floated upward. This process created Earth's three major layers: the core, the mantle, and the crust. The outer core remained liquid, while the inner core became solid due to the immense pressure. As molten iron continued to move inside the outer core, it generated powerful electric currents, creating Earth's magnetic field. This invisible shield still protects our planet from dangerous charged particles carried by the solar wind. Without it, Earth's atmosphere could have slowly been stripped away, making life far less likely. But Earth's greatest collision was still yet to come. Around 4.5 billion years ago, a Mars-sized protoplanet known as Theia slammed into the young Earth. The impact was so violent that it vaporized huge portions of both worlds. Most of Theia's iron-rich core merged with Earth's core, while billions of tons of molten rock were blasted into orbit. Over time, this debris came together under gravity to form a single natural satellite, the Moon. Scientists support this idea through the giant impact hypothesis, because the rocks brought back by NASA's Apollo missions have nearly identical oxygen isotope signatures and basalt composition to rocks found on Earth. This strongly suggests that the Moon formed from material that once belonged to our own planet. That single collision permanently changed Earth's future. It helped stabilize our planet's rotation, influenced its axial tilt, and created the tides that would shape Earth's oceans for billions of years. From a cloud of dust, to a blazing star, to a molten world, to a planet with oceans, continents, a protective magnetic field, and a moon, Earth was finally ready. But it was still completely lifeless. So the biggest mystery was only just beginning. How did non-living chemicals become the first living cell?